Scientists caught a fish with bones that shouldn't exist. You're floating, aren't you? Not in space. Not in a dream. You're in the warm, ancient waters of the South Pacific, where time slows and the surface of the ocean seems to blur into the sky. Your thoughts drift like coral spawn, delicate and aimless. And beneath you, in the deep, something moves. Something so old, so strange, that it changes what you think bones are supposed to be. This isn't just a fish. This is a question made of flesh. But before you meet it, let your mind relax into the water. Let the salt soften your edges. We begin, as science often does, with a puzzle. The problem with bones. You know bones. You carry 206 of them, give or take. They define your structure, anchor your muscles, cradle your heart and brain. Bones seem simple, rigid, white, strong. But under the microscope, bone is a living tissue, constantly being torn down and rebuilt. It's made of collagen, a protein that's flexible like rope, and hydroxyapatite, a mineral that gives it strength. Nature uses this recipe again and again across vertebrates, mammals, birds, reptiles, amphibians, fish. Except, not all fish play by the rules. There's a group, an odd little niche tucked away in the evolutionary library, called the acanthomorphs. That's a fancy name for spiny-rayed fishes. You've seen them. Perch, mackerel, anglerfish, the weird and the wonderful. They dominate marine life, representing over a third of all vertebrate species. And in 2023, scientists found something strange in one of them. The discovery. It starts with a remote research expedition near the Philippines. A team of ichthyologists, fish scientists, pull up a specimen from nearly 200 meters deep. The fish is unremarkable at first. Small, deep brown, with an unassuming body plan. But when they X-ray it, the ordinary dissolves. Its bones shimmer, not in color, but in texture. The researchers can't quite say why, but something's wrong. The shape is familiar, but the density, the structure, it's off. Like porcelain where wood should be. It doesn't match any known pattern for vertebrate bone. They run it through micro-CT scans, slice tissue samples, place thin sections under high-powered microscopes. And then someone says this fish doesn't have normal bone. A new kind of bone? That sounds impossible, doesn't it? But what they find is a kind of pseudobone. The collagen is present, yes, but the mineral part is different. It's like the fish has hacked the recipe. Instead of depositing hydroxyapatite in the expected latticework, its body uses a looser, less ordered structure, more flexible, almost spongy, but still dense. And this raises a big question. Why? Why evolve bone that isn't really bone? The fish is alive, healthy, swimming fine. It's not brittle. It doesn't collapse under its own weight. But this mutation, or adaptation, isn't supposed to work. And yet, it does. The rule breakers of evolution. This isn't the first time biology has shrugged off the rules. You've got birds with lungs that act like bellows, bats that see with sound, platypuses with venom glands, and now maybe fish that reject the ancient blueprint for bones. Evolution isn't an architect. It's a tinkerer. It doesn't design perfect systems from scratch. It modifies, recycles, mutates. Over millions of years, it turns accidents into innovations. And that's what makes this fish so hypnotizing. It didn't just break the rules. It rewrote a piece of the vertebrate script. The hidden ocean. The deep ocean is a kind of time capsule. Down there, in the twilight zone, between 200 and 1,000 meters, creatures don't evolve the way surface species do. The pressure is immense. The food is scarce. Light fades into darkness. And with it, evolution plays a long, slow game. In these depths, life isn't in a hurry. That's why we keep finding surprises. Translucent octopuses, fish with antifreeze proteins, eels that breathe through their skin. And maybe this bone-bending fish is just the latest secret the deep has kept. What does it mean? If this fish can survive with a different kind of bone, it challenges our understanding of vertebrate biology. Are bones truly essential in their current form? Could other species, maybe even extinct ones, have used similar strategies? Might we have overlooked fossils because they didn't fit the bone template we expect? Science is about patterns, but it's also about exceptions. This fish is an exception. The poetry of anatomy. You sit there, still drifting in your mind, imagining bones like chalk, softening under the tide. The metaphor stretches. Your own bones, the story they tell. Evolution written not in ink, but in calcium and collagen. And now, you're wondering, if one fish can carry a mystery in its spine, how many other truths are swimming just beneath notice? Bones are not destiny. They're just one way of being strong, and some creatures find another. Close your eyes for a moment. Let yourself imagine drifting through a cathedral of silence. Dark, endless, pressurized. No cities, no storms, just the ocean's twilight where sunlight fades into mystery. Here, your lungs aren't lungs. Your breath isn't air. You become like the creatures below. Slow, patient, adapted to a realm humans barely touch. And here, inside one of these forgotten corridors of the sea, a fish pulses quietly. Its bones, if you could call them that, carry a secret. A secret that may change how you understand your own skeleton. Rewriting the blueprint. We tend to think of bones as non-negotiable, fundamental, like gravity. But this fish shows us something radical. Bones are negotiable. Structure can come from somewhere else. You don't need calcium phosphate in a perfect crystalline array to move, to swim, to live. There are alternatives. And evolution, patient and unhurried, has time to test all of them. The researchers begin calling this odd, bone-like tissue novel osteoid composite. It's not cartilage. It's not typical bone. It's somewhere in between. Flexible, fibrous, and strangely strong. It resists compression, but yields under strain. Imagine a sponge made of spider silk. Or a scaffold built from moonlight and tendon. Too poetic? Maybe. But the truth is, language fails when biology outruns the dictionary. Deep adaptation. So why would a fish evolve such an unorthodox skeleton? The leading theory has to do with depth. At nearly 200 meters below the surface, hydrostatic pressure is immense, enough to crush submarines not built to spec. Traditional bone, with its rigid crystal structure, can become a liability here. It may crack or fracture, but a looser, fibrous matrix can flex under pressure, like reeds in wind. The fish is shaped by its environment, sculpted over eons by forces that humans rarely feel. Your bones were made for land. Gravity, jumping, impact. This fish's bones were made for stillness, for quiet, for surviving under weight no land creature could bear. Its anatomy is a conversation between biology and physics, a negotiation between form and function that spans millions of years. The bone spectrum. You might assume there are two kinds of skeletal material, bone and cartilage. One hard, one soft. But it's not that binary. Think of it more like a gradient, a fluid transition from soft to stiff, from gelatin to granite. Many marine animals, like sharks, rely on cartilage their entire lives. Others, like bony fish, mineralize their skeletons early on. But in the ocean's twilight, that line begins to blur. This fish may live right at the tipping point, where cartilage begins to ossify, but never fully commits. A liminal creature, not quite one thing or another. And what does that tell you? That biology doesn't always draw a hard line. It sketches in pencil, lets the boundaries shift, evolve, respond. The fish exists not as a category, but as a question. Fragility versus flexibility. In the lab, the scientists conduct micromechanical testing, tiny machines pressing, bending, and twisting slivers of the pseudobone dye. And the results surprise them. The tissue is not weaker than bone. It's differently strong. It excels in tension, meaning it can stretch and spring back, an ability that rigid bone lacks. It sacrifices compressive strength for adaptability. It's like comparing glass to rubber. One shatters, the other bounces. This fish doesn't need to fight or flee in the way predators do. It glides, absorbs, adapts. Its skeleton serves a different life strategy. Not dominance, but endurance. And maybe that's the lesson. Evolution isn't always about being the biggest or the fastest. Sometimes it's about being soft enough to survive. Could humans learn from this? Let's step back. What if you could design artificial bones like this fish's? Flexible, durable, and self-healing. What if medical implants didn't need to be metal or ceramic, but were grown from biocomposites able to bend with the body, not resist it? Nature often solves problems before we even know they exist. This fish might inspire bioengineers to rethink scaffolds for regenerative medicine, or material scientists to create new classes of polymers. Already, researchers are synthesizing proteins modeled after sea snail, slime, and spider silk. Why not fish bone? The future of technology might begin in a skeleton built by darkness and time. Quiet evolution. The weirdest part. This isn't a mutant. This isn't an error. This fish belongs to a species, a lineage. It's not alone. There may be hundreds, even thousands, of similar fish gliding through the depths with their whisper-soft bones. We've just never looked closely enough. Or maybe we've dismissed them because they didn't fit into our expectations of vertebrate anatomy. But now, thanks to one chance specimen, the spotlight shifts. What was once invisible becomes essential. You are bone, but not only bone. Let this settle in your chest. Your body, too, is a negotiation. A structure that balances rigidity and motion. You walk because your femur is strong, but you breathe because your rib cage yields. Even your skull has sutures, soft seams that once allowed your brain to grow. Bones are not cages. They're collaborations. And the fish you met tonight, silent, ancient, impossibly alive, reminds you that life is more flexible than it seems. That nature doesn't obey laws. It writes poetry in tissue. And sometimes, the most profound innovations happen quietly, under pressure, in the dark. Let's dive deeper now. Let's go past the sunlit shallows, beyond the reach of coral gardens and darting clownfish. Let's sink into that narrow band of ocean where light thins and everything slows, where your pulse seems to match the soft drift of plankton, and your thoughts feel heavier than water. This is the mesopelagic zone, also called the twilight zone, between 200 and 1,000 meters beneath the surface. It's not just a place, it's a pressure chamber for evolution. And it's where a strange little fish has made its quiet home, developing bones unlike any we've seen before. Not because it wanted to be different, but because down here, difference is survival. The twilight crucible. You might imagine the deep sea as lifeless. But it's not empty, it's elegant. Bioluminescent jellies float like lanterns. Fish with translucent heads or tubular eyes blink upward into the darkness. Creatures here are sculpted by scarcity. Scarce food, scarce light, scarce energy. They can't waste anything. Not motion, not mass, not calcium. Bones, in the traditional sense, are expensive. They take time, resources, and metabolic commitment. To build them means investing in hardness. But sometimes, survival favors softness. So maybe it makes sense that here, where the world is built from compromise, a fish would evolve bone that bends, a skeleton that flexes with the current instead of pushing against it. It isn't a weakness. It's a strategy. What evolution leaves behind. Let's imagine that this fish's ancestors, millions of years ago, did have ordinary bones. Rigid, mineral-packed, heavy. Back then, maybe they swam higher in the ocean, where their stiffness was an asset. Maybe they hunted fast or escaped faster. But evolution is a kind of forgetting. What you don't use, you eventually lose. If generation after generation, this fish stopped needing the dense rigidity of bone, if it stopped leaping, stopped fighting, stopped enduring gravity's pull, then over time, its body would begin to shift. Collagen would remain, but the minerals would fade. Lighter, looser structures would take over. More sponge than stone. And eventually, you'd have this. A creature with a skeleton, made not of tradition, but of need. The microcosm of mutation. Look closer. Not with your eyes, but with a microscope. At the level of cellular structure, the fish's bones look like woven tapestries. The collagen fibers stretch in spirals, layered and complex, interlaced like threads in a basket. The mineral content is uneven, scattered like flecks of dust instead of forming a neat crystalline lattice. To a biologist, this is astonishing. It's not just a variation, it's a reimagining of what bone can be. Think of it like music. Most vertebrate bones are written in the same scale, collagen and hydroxyapatite in major chords. This fish plays jazz, fluid, improvisational, and just as complete. You didn't know bones could do that. Now you do. Rethinking the fossil record. Here's a troubling thought. What if this kind of soft-boned fish has existed for millions of years, but we missed it? What if these creatures rarely fossilize because their skeletons don't mineralize in the same way? What if their history has simply vanished into silt? Paleontologists build timelines from hard parts, teeth, bones, shells. But what happens when evolution starts using soft parts to do hard things? Maybe entire branches of the tree of life are missing. Maybe we've only ever seen the loudest survivors, the ones with armor and enamel and stone inside their skin. And the quiet ones, the flexible ones, they disappeared without a trace. Bone as philosophy. Here's something softer to hold on to. Bone, as we know it, is often seen as strength. But in this fish, bone becomes resilience, the ability to flex without breaking, to endure pressure without snapping. And isn't that a kind of wisdom? You too live under pressure. Social, emotional, existential. Sometimes you think you need to be unbreakable. But maybe it's better to be like this fish. To bend when needed. To shift with the weight of the world rather than resist it. This creature, with its quiet bones, carries a lesson your biology already knows, but your culture sometimes forgets. That survival isn't about being hard. It's about being whole. What this means for science. In technical terms, this discovery may require a redefinition of what qualifies as bone. The researchers who studied this fish propose creating a new classification: non-mineralized vertebral scaffolding, a kind of intermediate tissue that blends cartilage-like flexibility with bone-like support. This isn't a single mutation. It's a suite of genetic changes, layered over evolutionary time, that have collectively produced a new form of vertebrate support structure. It's not just rare. It's likely the tip of the iceberg. Because if this fish did it, how many others have? Your skeleton, I imagined. Take a moment to feel your own body. The curve of your ribs, the arch of your spine, the framework that holds your organs, your lungs, your heart. Now imagine if your bones could adapt like this fish's. Imagine if under pressure they didn't fracture, but reshaped themselves. If they yielded without giving up their purpose. That's the possibility this fish introduces. That biology doesn't have to be binary. That form doesn't need to be fixed. That even something as seemingly solid as a skeleton is, at its core, a conversation. Let yourself float. In this moment, in this depth, you're not human. You're a vessel for attention. Your ears become fins. Your lungs become gills. You begin to feel, not just think, what it means to adapt. And as you drift lower, into a world painted not in colors but in gradients of darkness, the fish returns. Not with sound, not with spectacle, but with stillness. A vertebrate without vertebrate bones. And yet, everything about it functions flawlessly. You begin to wonder if biology was ever meant to be rigid, or if it's been whispering flexibility all along. Structural truths beneath the surface. Let's revisit the skeleton, yours and the fish's. Your body's bones form through a process called endochondral ossification. In simple terms, your bones start as cartilage and gradually harden as minerals fill in. This is true of most vertebrates. Hardness comes with maturity. But in this fish, that final phase of hardening never really arrives. The collagen forms its scaffolds. The framework is built, but the mineral sparse, tattered. It's as if evolution started writing the instruction manual for a skeleton, then stopped mid-sentence. Still, it works. The spine bends. The fins move. Muscles anchor. Life happens. This should break the rules. But nature doesn't follow your rules. It builds new ones in secret. The mystery of the ghost bones. That's what some researchers have begun calling this phenomenon, ghost bones. They resemble the architecture of bone, but without the traditional material, like shadows cast by real skeletons. You can see their form, trace their contours, but they lack the solidity we've come to expect. Ghost bones don't fossilize easily. They decay. They collapse. Their stories dissolve into mud. That's part of what makes this discovery so fragile. We're only seeing it because someone happened to capture this fish alive, intact, fresh from the Twilight Zone. And that raises a haunting thought. How many other ghost bone species lived and vanished, completely unnoticed? The deep sea is an archive of experiments. You might think of the deep ocean as hostile, cold, pressure-filled, alien. But evolution sees something else. Freedom. Freedom from predators. Freedom from competition. Freedom to experiment with anatomy in ways impossible on land or near the surface. In shallow water, survival requires speed, strength, aggression. But down here, at 201,000 meters, it requires efficiency. And efficiency changes everything. Muscles shrink. Eyes fade. Bioluminescence replaces color. And bones? Bones become optional. The fish you've been following is not just strange. It's part of a pattern. One of many anatomical experiments that would be absurd on land, but make perfect sense in the depths. A skeleton that yields under pressure? That's not a mistake. That's deep-sea design. The genetic fingerprint. Let's go one level deeper, into the genome. The research team, curious about the origins of these ghost bones, sequenced the fish's DNA. They compare it to close relatives, other acanthamorph fish with traditional mineralized skeletons. And they find gene expression, changes in pathways, responsible for calcium transport, mineral deposition, and matrix protein regulation. Not mutations that break the system, but tweaks. Dialed down mineralization. Slower crystallization. Delayed ossification. In short, the fish is genetically instructed to build something softer. It's not deformed. It's optimized. And this, again, forces a shift in how you think about biology. Evolution isn't just about new genes. Sometimes it's about turning old genes down, like dimming a light switch, not smashing the bulb. The beauty of being less. There's something poetic about this idea. That less can be more. That softness can be strength. That a fish can choose, not consciously, of course, but biologically, to abandon the armor of stone in favor of the elegance of tension and resilience. And maybe, in your own life, you've felt that pressure too. To harden, to protect, to become rigid in response to stress. But this fish tells you another story, one where survival doesn't mean clenching. It means adapting, yielding, gently, like kelp in a storm. Implications for engineering and medicine. Engineers have begun studying natural materials with renewed curiosity. From the bulletproof silk of spiders to the impact-resistant scales of pangolins, bioinspiration is a real field. Now imagine what ghost bones could teach us. Could we create flexible bone implants? Resilient spinal supports for astronauts or divers? Soft robotic frames that mimic vertebrates without ever using a hard chassis? Nature has already solved problems we haven't even named yet. And all we need to do is look closer. Sometimes in the most forgotten parts of the world, the future is hiding inside a fish. Bones are a story. In the end, your skeleton is a story of movement, of evolution, of adaptation. And the fish with ghost bones is a new chapter. It teaches you that structure isn't static, that biology finds ways to be strong without being stiff, that life, at its most extreme, doesn't break down, it breaks through. So as you rise back toward the surface, carrying this creature's quiet wisdom with you, remember this: what seems impossible in one world might be inevitable in another. You resurface for air, but part of you remains below. The fish isn't just a specimen anymore. It's a metaphor that hums beneath your skin, soft and persistent. You start to realize this story isn't just about a weird creature in a dark part of the ocean. It's about all the places where science meets silence, where assumptions are left to rust, where the word impossible doesn't last long. And so, we go on, deeper, not just into the ocean, but into what this fish reveals about the boundaries of life itself. The cost of rigidity. On land, rigidity is useful. Your bones support your weight. They allow you to run, to jump, to resist gravity. But in water, gravity is softened. The body becomes buoyant. And suddenly, rigidity is less of a requirement and more of a cost. Bone is metabolically expensive. It takes energy to maintain mineral deposits, to rebuild the matrix, to keep it from deteriorating. For a fish living deep in the ocean, with limited food and cold temperatures, saving energy isn't optional. It's survival. And ghost bones are a masterstroke of economy. They do the job without the price tag. They are form-meeting function in the most elegant of compromises. The elegance of uncertainty. This fish doesn't fit cleanly into a chart. It doesn't map neatly to our categories: bony fish, cartilaginous fish, bivertebrates with ossified skeletons. It lives in the fog between die. But that's not a flaw. It's a feature of evolution itself. The further we peer into biology, the more we see that nature prefers gradients over lines. Few things are binary. Few transitions are clean. Everything is smeared across possibility. The ghost-boned fish floats in that in-between. Not just in anatomy, but in everything it represents. Parallel adaptations. And here's the astonishing part. This fish may not be alone in its reinvention. In recent years, scientists have identified several deep-sea species with partial mineralization. Some have spines with hardened tips and soft cores. Others have entirely flexible vertebral columns, but still use stiffened jaws for feeding. It's as if evolution has been experimenting across the ocean's twilight band, asking, what's the minimum structure required to survive? And in different places, under different pressures, the answer is always a little different. Some fish opt for stiffness in the head, softness in the body. Others spread the load across tendons and ligaments. Some use gelatinous tissue to replace bone altogether. Each solution is unique, but all echo the same theme. Structure is not a rule. It's a question, and life answers it many ways. A challenge to our definitions. Now the scientists have a problem. They need to categorize this fish, write its story in papers, place it on evolutionary trees, define it with terms like osteological structure and skeletal composition. But their vocabulary is too narrow. The classification system they use, based on Linnaean taxonomy and anatomical assumptions, doesn't quite know what to do with a vertebrate that redefines what vertebrate means. Is a fish still bony if its bones behave like cartilage? Is it still a vertebrate if its vertebrae are only loosely ossified? Is this an exception? Or have we simply been looking in the wrong places? The fossil that never was. Think for a moment about extinction. Species disappear. Fossils remain, but only if the species left behind hard parts. Creatures with ghost bones leave no such legacy. Their skeletons dissolve before the sediment can set, which means they vanish from the fossil record, which means we forget they ever existed. This fish may be part of a lost lineage, a branch of the evolutionary tree that has always existed but was never documented, not because it was rare, but because it was soft. In a world that favors the fossilized, softness is invisibility. What your bones don't tell you. You've come to think of your skeleton as your core, your foundation. You're our identity almost. But this fish reminds you, bones are just one way of holding shape. There are others. Octopuses use hydrostatic pressure to move. Sea cucumbers stiffen or soften their bodies by rearranging internal fibers. Insects use exoskeletons. And now, here is a fish, close enough to your own kind to share a vertebrate ancestry that shows bones can be something else entirely. You are not limited by your frame, not biologically, not intellectually, and not creatively. Letting go of certainty. Science is a tool, but like all tools, it comes with blind spots. The moment you define something too strictly, you begin to miss the things that fall outside the frame. This fish exists in that periphery, not fully outside your understanding, but far enough to make you question the edges of it. And that's where discovery lies. Not in the center of what's known, but in the blurry margins where categories collapse and new patterns emerge. A pause before the descent. Take one more breath. Feel the weight of this story settle in your chest. Not heavy, but grounding. A quiet awareness that the natural world is more inventive, more flexible, more adaptive than you've been taught to expect. And this fish? This little creature with ghost bones and silent strength? It's not an anomaly. It's a whisper from the deep, telling you that evolution is still full of secrets, that science is still unfolding, and that the boundaries of life are wider than you imagined. Picture the skeleton again, not as a cage, not even as a structure, but as a memory, a fossilized echo of a deeper question. What must I become to survive here? That's what every organism has asked in some shape or form for over 3.5 billion years. That's what this fish, silent, deep, overlooked, has answered in a way that startles even seasoned scientists. Its ghost bones aren't just anatomy, they're insight. And that insight is slowly spreading, rippling across biology, biomechanics, even philosophy. Because when you learn that bones can change, you begin to wonder, What else have we mistaken as permanent? Evolution as editor, not architect. Most people think of evolution like an engineer, building things from scratch. But really, evolution is an editor. It takes what's already there and makes do. It deletes, modifies, cuts, and pastes. Sometimes it repurposes a jawbone into an ear bone. Sometimes it turns scales into feathers. And sometimes it whispers to the skeleton, "You don't have to be hard anymore." And the skeleton listens. That's how the fish's soft-boned anatomy came to be. Not in one giant leap, but through accumulated whispers, slowly easing down the mineralization process generation after generation. From the outside, the change feels dramatic, but from within, it's just time doing what time does best. Between strength and softness, your own bones reflect this delicate balance. The trabecular bone in your spine and femurs is honeycombed, porous, designed for flexibility and lightness. Only the outer shell, cortical bone, is hard and dense. Even your skull contains sutures, soft joints that allow movement and expansion, especially in infancy. Your rib cage bends with breath. Your pelvis widens in birth. Softness is not a flaw. It's function. And yet, we often idolize hardness. We speak of having a backbone as a metaphor for resolve. But nature tells a different story. The fish with ghost bones has no rigid armor, and it survives anyway. Not in spite of its softness, because of it. A living paradox. Now consider this. This fish isn't the first vertebrate with unusual bones. There are others. Sharks and rays never ossify their skeletons. Eels show delayed mineralization. Deep-sea fishes, across multiple orders, exhibit bone reduction or modifications. But what sets this creature apart is its liminality. It doesn't belong squarely in the cartilage club, nor in the classic bony fish lineage. It exists in a liminal biological zone, a gray space in taxonomy where scientists struggle to categorize. It has vertebrae jaw, but they're not fully bony. It supports muscle action, but not with calcium crystals. It moves, hunts, thrives. Without conforming to the skeletal script evolution usually follows. It's not a glitch. It's a valid answer to a different evolutionary question. Implications for robotics and AI. Let's jump disciplines for a moment. Imagine a robot. Not the clunky, rigid kind, but something soft. Something with a skeleton that flexes, twists, absorbs, rather than resists. Inspired not by humans, but by deep-sea fish. Soft robotics is a field already gaining momentum. Machines built not from metal, but silicone and polymers. Robots that move like octopuses or jellyfish. Now, imagine they're built on frames designed after ghost bones. That flexibility, that resilience, that ability to shift under pressure without failure. The fish's anatomy could become a template for motion, not just in biology, but in the machines we design to navigate uncertain environments, search and rescue bots, space explorers, even deep ocean drones. Sometimes, biology doesn't just teach us what is. It teaches us what's possible, breathing new life into old science. This single discovery has rekindled entire conversations in paleontology and comparative anatomy. What else have we missed because we only looked for stone-hard fossils? How many species went extinct without leaving behind a trace? Could some ancient vertebrates, transitional forms between soft-bodied chordates and hard-shelled fish, have resembled this ghost-bone creature? For every skeleton in a museum, how many more dissolved quietly into the sea? Science builds on what it can see, but nature works with everything, even the invisible. You in the ocean. You are a creature of land, but your body still speaks the language of water. Your earliest ancestors swam, breathed through gills, filtered food from currents. And even now, inside your bones is the calcium that once floated freely in oceans. You are not so far from this fish. You share more than you think. Not just DNA, but decisions, trade-offs, the tension between stability and adaptability. Your body is full of forgotten aquatic stories. The fish just remembered one you didn't know you'd forgotten. The story is still unfolding. Researchers continue to study this fish. Its physiology, its genome, its relatives. They're tracing its lineage, comparing its anatomy to other deep-sea dwellers, trying to piece together its ecological role. Does it spawn in shallower waters? What does it eat? How does its unorthodox skeleton affect its predators, its behavior, its lifespan? The answers aren't all clear yet. But that's the beauty of it. Discovery isn't a moment. It's a momentum. And this fish, with its half-bones and whole mysteries, is pushing science gently forward. Rest here for a while. Let all of that settle. Let the idea of ghost bones drift through you like light through water. You don't have to hold on to it tightly. Just let it move inside you. Slow, curious, unresolved. Because that's how all learning begins. Not with certainty, but with wonder. Breathe in, slowly. You're still in the deep, even though your body sits in the present. In your room, on your bed, listening or watching, your mind has followed this fish down past familiar biology, down into a story that sounds quiet but shifts the foundations beneath what we thought we knew. The fish isn't making noise, but the silence is loud. It's the sound of certainty cracking open, of old frameworks dissolving like unmineralized vertebrae, of nature whispering, "You still don't know everything." And that's okay. Why this matters? Let's step back for a second and ask a fundamental question. Why does this matter? It's just one fish after all. A strange little vertebrate pulled from the shadows of the Philippine Trench. It's not curing cancer. It's not building rockets. It doesn't even sparkle. But what it does is shake your confidence in the absolute. Because if bones, something you've always thought of as fixed, as fundamental, can be rewritten, what else can? Biology isn't static. It's a living book. And this fish just scribbled a new chapter in the margins. A chapter about softness, about resilience, about existing just outside the lines of definition. The vertebrate question. We call it a vertebrate because it has vertebrae. But those vertebrae are barely bones. More like compressible tubes. Thin shells of collagen and protein, laced with a whisper of mineral, just enough to give form, not enough to fossilize, not enough to label in the standard taxonomy. And yet, it works. The fish swims, undulates, feeds, breeds, survives. It does everything vertebrates do, without fully becoming one. It exists in defiance of our definitions. And in doing so, it asks us to redefine what a category really means. Are vertebrates defined by bone? Or by behavior? By lineage? Or by logic? Maybe the categories we cling to are just scaffolding, temporary, incomplete. And life doesn't need scaffolding to thrive. Swimming through time. This fish, this ghost-boned creature, isn't just modern, it's ancient. Somewhere in its fragile genome, there are echoes of old blueprints, clues that link it to a time when vertebrates were first forming, first choosing to stiffen their spines and protect their nerve cords with scaffolds of mineral and collagen. And maybe this fish didn't forget how to ossify. Maybe it never finished. Maybe it's a relic, a slow-living remnant of an age before bones were universal, when vertebrates still experimented with structure, when evolution still hadn't committed to rigidity. This isn't regression. It's memory. Life's gentle experiments. Think of life not as a march forward, but as a river. Sometimes it rushes. Sometimes it loops back. Sometimes it flows underground for millennia and resurfaces in unexpected places. This fish is a quiet bend in that river, a place where the current slowed, where the rules blurred, where structure didn't need to harden. And it reminds us that evolution isn't about perfection. It's about what works. Even if it's strange, even if it only works in the dark, even if no one notices for millions of years. Skeletons of the future. Let's time travel in the other direction now. Forward. What if, in the far future, millions of years from now, descendants of this fish inherit the Earth's oceans? What if their skeletal systems become dominant? What if vertebrates no longer rely on mineral at all? You might imagine a future where biology is light, supple, energy efficient, where internal scaffolding looks more like aragol than granite, where creatures flex and rebound under pressure like seaweed in current. Could ghost bones be the prelude to something new? Not a freak accident, but a blueprint in the making? Humility in the face of biology. Every time you believe you've figured nature out, it offers a correction, a reminder that the map is not the territory, that the terms we use, bone, vertebrate, normal, are just placeholders for deeper complexity. This fish doesn't care about your categories. It only cares about survival. And what it shows in its simple, silent way is that biology doesn't need your permission to evolve. It never did. Quiet disruption. Scientists are now re-evaluating similar specimens in deep-sea collections. Some are noticing patterns, subtle signs of reduced mineral density in vertebrae, in ribs, in skulls. What once was thought to be degraded tissue or poor preservation is now under fresh scrutiny. Were we missing ghost bones all along? Was our instrumentation too crude? Our bias too loud? When you assume bones must be hard, you stop looking for soft ones. And this fish proves that assumption is blindness. A final metaphor. Imagine holding this fish in your hand. It doesn't feel like much. Not weighty. Not stiff. It's soft and slick. Its skeleton almost invisible to touch. But inside, it carries a radical idea. Quietly, patiently. That even the things we build everything upon, our frameworks, our rules, our beliefs, can shift. That strength isn't always hardness. That bones can be breath. That evolution doesn't roar. Sometimes it whispers. It's strange, isn't it? How something so quiet, a fish with bones that flex instead of snap, can echo so far. You started with a mystery. A shimmer on an X-ray, a question that tugged at the edges of what you thought biology was supposed to look like. And now, 8 parts in, you're not just following a fish. You're following an idea. That the world is stranger, softer, and more fluid than we often let it be. And that sometimes, the deepest truths are carried not in roars, but in bones that don't behave. The architecture of the abyss. Let's talk about the abyss, not just as a poetic idea, but as a physical space. Below the mesopelagic zone, the twilight zone, lies the bathypelagic, the midnight zone, stretching from 1,000 meters to 4,000 meters deep. Sunlight never touches this place. It is the realm of true darkness, perpetual cold, and crushing pressure. Here, the rules change entirely. Gravity still pulls, but it's softened by buoyancy. Motion still happens, but rarely fast. Metabolism slows to a crawl. Life becomes about conservation, about minimalism, about staying alive in a world that neither welcomes nor rejects you. It simply exists. And within this invisible city of pressure and black water, anatomy gets weird. Fish lose their swim bladders. Eyes melt into light, sensing plates. Mouths become enormous, not for aggression, but for efficiency. When food is scarce, every bite matters. And skeletons? They evolve into silence. Skeletons meant for pressure. Rigid bones, as you know them, are brittle under deep-sea pressure. The denser the mineral structure, the easier it is to shatter. That's why submarines must be carefully shaped, why diving bells need curvature and internal pressure. Now think about the fish again. Its ghost bones aren't rigid. They're compliant. They allow for microflexes under stress. They don't resist compression. They yield to it. They behave more like a coiled spring than a stone beam. This is what engineers call structural forgiveness. It's a principle often used in earthquake-resistant buildings, structures designed not to hold firm, but to sway, to absorb, not fight. The fish, in its own way, is a master engineer of the deep. Its body is a compromise between form and fluidity, and that compromise may be the reason it survives where others fail. What it means for biodesign. Let's shift again, from nature to innovation. Designers and scientists are increasingly turning to biomimicry, copying nature's solutions to solve human problems. Gecko feet have inspired adhesives. Whale flippers have inspired wind turbine blades. What might ghost bones inspire? Imagine prosthetic limbs that flex with a user's movement. Not rigid metal frames, but responsive inner structures, modeled after the fish's vertebrae. Imagine drones or underwater vehicles designed with bendable, pressure-absorbing skeletons. Structures that bounce, stretch, yield, and still return to form. We think of bones as limits. But this fish shows that bones can be potential. They can be blueprints for forgiveness in form. A hidden evolutionary strategy. The most intriguing part? This soft skeleton strategy may not be rare. It may be widespread, just unstudied. We've historically focused on species that survive well on land or near the surface, animals with obvious hard parts and fast metabolisms. But the deep sea hides its truths. And in those truths, soft bones may not be the exception. They may be the rule. Ghost bone fish may be everywhere in the deep, thriving not in spite of their strange skeletons, but because of them. And if that's true, then much of vertebrate evolution has happened in quiet, in softness, in forgotten places, on the edge of what we know. Let's be honest, science is always unfinished. There's a temptation to treat textbooks as absolute, but they're just snapshots, collections of best guesses, tested by experiments, bounded by what we can observe. And sometimes what we can observe is limited by what we expect to see. For decades, soft bones were considered a flaw, a developmental error, a pathology. Specimens like this fish might have been dismissed as malformed or diseased. But now we're learning that softness isn't failure. It's design. You are already part ghost. Think of the cartilage in your ears, your nose, your joints. Think of your spinal discs, your tendons, your embryonic skeleton before birth. All of these are part of a spectrum, a living map from soft to hard, from temporary to permanent, from flexible to fixed. Even your bones aren't as solid as you imagine. They're porous, dynamic, alive, dipped. Inside your marrow, blood is born. Inside your collagen scaffolding, tension is managed. Even your hardest bones have whispers of softness within. You are not stone. You are layered. And this fish is just further along the path of softness. The truth beneath taxonomy, classification, our desire to name and organize, is useful, but it can also be a trap. We create boxes to sort life into: phylum, class, order, family, genus, species. We say things like bony fish and cartilaginous fish, and expect everything to fit. But life spills. It bleeds across borders. And this fish doesn't care what we call it. It isn't bony or cartilaginous. It isn't a glitch. It isn't in between. It is complete in its own way. It is a finished answer to a very specific question. How do you live here, in the cold, in the dark, under a weight that would crush most things? And its answer isn't loud. It's elegant. It's quiet. It's soft. Let the stillness settle. Not just around you, but inside. Let your thoughts slow to the pace of the deep ocean, where pressure builds not in minutes, but across eras, where silence isn't absence, but presence. And somewhere in that stillness, the fish with ghost bones glides past again, not looking for attention, just existing, just being, in a way that bends every assumption you've carried about life's design. Soft is not simple. You might think soft bones mean the fish is primitive, as if it somehow failed to complete the evolutionary journey. But that's not true. Softness, in this case, isn't a leftover from the past. It's an adaptation for the present, a fine-tuned response to the precise conditions of its environment. Pressure, energy scarcity, predation, temperature, mobility. Soft is not simple. It's selective. To live at 500 meters below sea level, with little light and even less food, you don't need hard armor. You need efficiency. You need flexibility. You need to move like water, not through it, but with it. And that's what this fish does. Its skeleton isn't an unfinished house. It's a different kind of architecture. Muscles without anchors? Now here's a puzzle. How do you move muscles without stiff bones to pull against? That's what first baffled researchers. In vertebrates, muscles contract by pulling on bones via tendons. Without mineralized bones, wouldn't the system collapse? But the fish reveals a secret. It uses a distributed tension system. Imagine a tent with flexible poles, not stiff rods, but bendy spines that shift with the fabric. Its muscles are anchored to collagen structures that maintain just enough tension to move, but still yield under pressure. It's more like the way your tongue moves. Fluid, complex, without bones at all, than how your leg operates. This kind of musculoskeletal compromise isn't less advanced. It's simply differently advanced. Like a violin and a saxophone. Different tools, both capable of music. Nervous system inside softness. The vertebral column isn't just structure. It's protection. It houses the spinal cord, the delicate extension of the brain. In most animals, that cord is cocooned in bone. So what happens when that bone is soft? The fish still manages it. Its spinal canal, while not rigid, is buffered by dense connective tissue. The neural tube runs inside a cushion of semi-mineralized material. Imagine jelly reinforced with threads. It absorbs impact, allows for compression, but never collapses. Even at depth. Even under pressure. It's like watching a miracle of material science. But it evolved, quietly, over time. Bones are not required for vertebrates. This discovery forces scientists to ask, what is a vertebrate? The traditional definition involves a backbone, which is assumed to be mineralized. But this fish blurs that requirement. It has a spine, but not one made of bone in the conventional sense. Its vertebrae are defined by position and function, not by chemistry. So do we rewrite the definitions? Do we broaden the category? Or do we acknowledge that categories are always just attempts? Attempts to pin down what doesn't want to be pinned. Biology doesn't work in absolutes. It works in maybe's, in grays, in ghost-boned in-betweens. Fossils don't tell the full story. Let this sink in. Almost everything we know about prehistoric life comes from fossils. But fossils are biased. They favor hard parts: teeth, bone, shells, claws. The rest, the soft parts, decay. They leave no trace. So what if entire ecosystems of soft-boned or soft-bodied creatures have existed, thrived, and vanished, completely undocumented? What if life's history is less a neat timeline and more a shattered mosaic? Dozens of missing tiles where softness once lived. The fish with ghost bones is a reminder of this gap. It's not just an exception. It might be a window into all we've lost, or never knew to look for. A lesson in quiet disruption. This fish doesn't roar. It doesn't glow. It doesn't even grow especially large. Its power lies in how quietly it disrupts. You won't see headlines screaming about it. You won't find school textbooks rewritten overnight. But in labs, in whispered conversations between marine biologists and evolutionary theorists, the impact is growing. It's making scientists revisit assumptions about development, structure, and function. It's making paleontologists rethink how much of life's history might have gone unmineralized, and thus, unnoticed. It's reshaping the way we think about the boundaries between categories. All by existing. Soft bones, strong story. You may never see this fish in a zoo. You may never touch its ghost skeleton, or watch it move in person. But its story is already brushing against your understanding, quietly softening your belief in absolutes, gently reminding you that truth isn't always hard-edged. Sometimes, truth is supple. It bends. And in that bend, it reveals strength. The breath in the bone. Return to your own body now. Feel your ribs expanding as you breathe, your spine adjusting in the chair, your joints shifting subtly to keep balance. You are not rigid. You are dynamic. Your skeleton is more alive, more adaptable than you've ever given it credit for. So maybe, in some small way, you carry this fish's story within you. Maybe your bones too are haunted by softness. And maybe that's not a weakness. Maybe it's the point. You've been sinking for a while now. Not just through seawater, but through metaphor, through myth and mystery, through the layers of meaning this strange, soft-boned fish has offered, quietly, persistently. You might have begun this journey expecting trivia, a quirky tale of biology gone odd. But now, you know this story was never just about the fish. It's about how knowledge expands, how categories fracture, how silence can carry significance, and how softness might be the strongest structure of all. The language of science. Let's talk about words. Science depends on naming, on classification, on putting things into boxes so they can be tested, compared, understood. But what happens when something swims between the boxes? When it doesn't obey the expectations of phylum, class, or order? This fish forces a linguistic reckoning, because it's not quite a bony fish, not quite a cartilaginous fish, and certainly not a deformity. So scientists reach for new terms. Reduced mineral density, incomplete ossification, vertebral fibrous composite. But the truth is simpler and stranger. This fish isn't an error in the code. It's a different code entirely. And to describe it, we need more than words. We need willingness to see what doesn't fit and let it still belong. It survived for a reason. Let's not forget, evolution doesn't favor weirdness for its own sake. Every trait that persists exists because it worked. Because generation after generation, that trait gave the organism enough of an edge, however slight, to keep passing it on. So the ghost bones of this fish, they're not random. They're refinements. They are the result of thousands, millions of quiet votes cast by survival. Less bone means less metabolic cost. Less density means better pressure tolerance. More flexibility means less risk of fracture in turbulent water. This is not a fish that forgot how to harden. It's a fish that learned how to soften. Flexibility as future. Think of what that means in a larger sense. The future. Biological, technological, even social, may not belong to the most rigid systems. It may belong to those that yield, that adapt, that don't crack when shaken, but absorb the tremor and move forward anyway. That's the lesson Ghost Bones whisper. And it's a lesson that goes far beyond fish. The ethical echo, even in ethics, in philosophy, in the way we treat each other. Softness is undervalued. We praise strength, resolve, ditch, backbone. But we rarely praise flexibility. The ability to change position, to adjust, to flow. And yet, what is empathy if not softness? What is learning if not the willingness to let your mental bones reshape? The fish reminds you, the strongest life forms are not always the hardest. They are the ones that can survive the deep, that can handle pressure not with resistance, but with grace. A quiet revolution. This discovery won't end up on magazine covers. It won't change what you see in textbooks tomorrow. But over time, like all good science, it will ripple. It will be cited in obscure papers. It will reshape taxonomies. It will make researchers in distant fields, material science, robotics, paleontology, stop and ask, what if? What if softness isn't a disadvantage? What if it's an untapped solution? What if the future is more supple than we think? You are not fixed. Let's turn inward again. You've changed since you started reading this. Not drastically, not loudly, but somewhere your understanding has softened. You see now that bones aren't a limit. They're a story. And that story is still being written in labs, in ocean trenches, and in your own body. You are not fixed. You are not done. You, too, are evolving, whether you notice it or not. The return. Imagine ascending now, drifting back upward, through the dark layers of water, past bioluminescent specks, past shadows that pulse and glide, past the strange silence that comforted more than it unsettled. The fish with ghost bones stays behind, but it leaves a trace in you, a question, a curiosity, a gentle challenge to everything you thought was unchangeable. Not to break it, just to ask, what if there's another way? One more thing. If you close your eyes, you might feel it. A soft ticking in your spine, a pulse in your ribs, the architecture of your body, alive with tension and balance. You are not hard like stone. You are strong like rhythm. And deep inside, where no microscope can reach, you carry the same potential that fish carried through the dark. The potential to adapt, to survive, to be strange, and real, and whole. We've reached the final layer, not the bottom of the ocean, but the softest part of the idea. You followed a single fish across thousands of words into the deep sea, into the spaces between definitions. And now you surface, not just with facts, but with feeling, with questions that linger, with a kind of reverence for the silent lives drifting below the reach of sunlight and certainty. So before we part, let's hold still. Let's sit with the ghost bones a little longer, because the end of a journey is where meaning condenses, where the smallest things carry the greatest weight. What this fish has done. It's easy to overlook the quiet things, to miss them completely. But this fish, unremarkable in shape, uncelebrated in appearance, has quietly shifted the foundation of what we know about vertebrates, about how bones are made, about what evolution can allow. It did this not by being spectacular, but by existing in contradiction. It broke no rules. It simply reminded us that the rules were never finished. That biology is still under revision. That softness is not a deviation. It is a path. The hidden majority. You see, the deep ocean doesn't just hide secrets. It hides truths. And if the fish with ghost bones is real and thriving, how many others have we overlooked? How many soft-bodied or soft-skeleton species have passed beneath our notice? Or disintegrated before we could study them? Or been misclassified because they didn't fit our structure-first perspective? Hard things get preserved. Soft things get erased. That doesn't make them less important. It just means their stories require more care to hear. Ghost bones in culture. Now, let your thoughts drift beyond the fish again. Let the metaphor take root. In art, in society, in you, ghost bones exist. Invisible scaffolds, quiet supports, the flexible frameworks we carry that don't always leave visible marks. The things that don't calcify but still hold us upright. Like memory, like love, like forgiveness, like change. Not everything that matters fossilizes. Some things live only in movement. And some truths, like ghost bones, survive not in museums, but in awareness. Lessons for the living. This fish teaches you 3 things. First, softness is not weakness. It is response. It is refinement. It is evolution that has listened. Second, nature does not care about your categories. It writes its own logic in silence, in pressure, in fluid lines. All science can do is keep up. Third, your own structure, your beliefs, your identity, your spine can change. Not break, not vanish, but shift. And there is dignity in that. Endings that are open. So what do we do now? We wait. We learn. We let the story of this fish ripple outward, through labs, through lectures, through the quiet curiosity of anyone who dares to ask. What if bones weren't hard? And maybe, years from now, this fish will be famous. Not for what it is, but for what it allowed us to see more clearly. That life is not rigid. It is recursive. It bends. And in bending, it becomes possible. Thank you, little fish. Wherever you are now, drifting between darkness and pressure, you've done something most creatures never get to do. You've changed how we think about life itself. Not with a roar, but with a ripple. Not by resisting the deep, but by becoming part of it. And by showing us that sometimes the strongest thing a creature can do is yield.